Okay, let's take a look at some of the series expansions that we know from last year. And in this video, we're going to introduce the topic, which is where we evaluate a limit. Now, you will have done some limits already at this point, but some of the functions that we're going to evaluate the limits for are quite a bit more complicated than what you'll have done so far. Okay, so if you think about it, if we were asked to evaluate the limit as x tends to 0 of cos x, you can do that by inspection. Like, if you think about the cos graph, as x tends to 0, so as the values get smaller and smaller, you can see that the cos graph is going to tend to 1. Okay, I mean, you could try it on your calculator, you could work out like cos of 0.0001, and like as x, like all this means is x is getting smaller as we get closer. Like if you think about this as your x-axis, as the values get closer to 0, what does the answer get closer to? And if you work out cos of something really small, you're going to be approximately the same as the number 1, aren't you? So using this notation, you could say as x tends to 0, cos x tends to 1. But when we actually write it as a limit like this, we're allowed to say, well, the limit is equal to 1. So don't say tends towards when we set it out like this. We say as x tends to 0, this limit would be equal to 1. Let's look at the next one. So what would happen as x tends to 0 to the square root of x? Now if you think about it, if you know what the square root graph looks like, it's like the inverse of a quadratic, isn't it? So like if you think about your quadratic graph, it's the inverse of that, and it's got this sort of shape. It does actually keep on increasing, like as x gets bigger, the square root gets bigger. It just does it quite slowly. But we're not thinking about as it gets bigger, we're thinking about as it gets smaller, so as it tends towards 0. And if you wanted, if you square root of like a really small number, that would essentially approach 0. The answer would be small. Can you see that from the graph as well? We can see that when you square root a small number, the answer that you get out is also small. So we could say that the limit as x tends to 0 of the square root of x would be equal to 0. This next one, I mean, have a look at it, but we're not going to be able to do this by inspection. Now, as x tends to 0, think about what happens. Sine of x also tends to 0, just from your sine graph. We can see that as x gets smaller, sine of x also gets smaller. Also, if you evaluate sine of a small number, you're going to approximate 0. Okay? So what we've got here is two things that are both tending towards 0. Essentially, we can't evaluate this by inspection because we've got something that's tending towards 0 divided by something else that's tending towards 0. And you might think, well, 0 divided by 0 is equal to 1, right? And I mean, coincidentally, that is correct for this question, but the limit's not always 1. When you end up with something tending towards 0 divided by something else tending towards 0, it depends on the speed, like how quickly the two things tend towards 0, and we can't just look at it and see what the answer is. The way that we're going to evaluate these more complicated limits is what we can do, is we can use series expansions. So if we look at this question, let me just write it out. So we can think about it as a series expansion. And for this first one, we know the shortcut. Like we know what sine x can be approximated as a polynomial. So we could say this would be the same as the limit as x tends to 0 of sine x, which is x, minus x cubed over 3 factorial plus x to the 5 over 5 factorial. all divided by x. And now essentially we can, because we've got a polynomial with a common factor, like each of these have got a factor of x in, and we're dividing everything divided by x, we can cancel down all the x terms and say that'll be the same as the limit as x tends to 0 of x divided by x, which is 1, minus x cubed divided by x, which would be x squared over 2 factorial, plus x to the 5 divided by x, which would be x to the 4. And this is an infinite expansion, like there's going to be x to the 7, x to the 9, and so on, but it doesn't matter that we don't have all of those terms, because all of those powers of x, as x tends to 0, like minus x squared over 2 factorial, that's going to tend to 0 as well, isn't it? Like as x gets smaller, x squared gets smaller, x to the 4 over 5 factorial. All that stuff is going to tend towards 0, so we can evaluate the limit. And all we're left with is the number 1. Okay. So what we're going to do now, we're going to have a look at a couple of exam style questions. We might just do one of them actually, so it'll take a bit of time. And it will use this Maclaurin series expansion. And we'll also tie it in with evaluating a limit at the end. Okay, so let's look at the example. And this is like a standard exam style question. First part of the question says use the series expansion for ln of 1 plus x to write down, we're not going to use the Maclaurin expansion, we're not going to like differentiate and sub-zero in, like this is a shortcut, we want to write down the first 4 terms in ascending powers of x for ln of 1 minus x. So if you think about the general formula that we know, the shortcut for ln of 1 plus x, we're being asked for ln of 1 minus x. So essentially, we could think about it as the x in this expansion is just equivalent to minus x. And use a bracket, like the bracket's important. Okay, so ln of 1 minus x would be x, which is clearly minus x, minus a half, x squared, which is minus x squared, plus a third, minus x cubed. How many do we need? First 4 terms. Okay, so minus a quarter, minus x to the 4. Just be really careful with your negatives. Okay, so ln of 1 minus x would be minus x. Minus squared is positive, but then we're multiplying by a negative, so minus a half, x squared. Negative cubed is negative, so minus a third. X cubed minus to the power 4 is positive, but then you subtract it, so minus a quarter x to the 4. The next part of the question is where Maclaurin's comes in, because it says the function is defined. So we've got a function which is f of x, which is e to the power of sine x. Now if you look at our shortcuts, we know a shortcut for e to the power of x, but unless you want to replace x with the sine x expansion, it's going to get messy. Like we're not going to use shortcuts for this one. This is where the general Maclaurin theorem comes in. Okay, so we're going to essentially sub-zero in, differentiate, sub-zero in again, and we're trying to approximate this function here as a polynomial. Okay, we want to get the first 3 terms, so we're going to use the function, the first derivative and the second derivative. So when we're using Maclaurin's theorem for a general function, first thing you need to be thinking is, well, I want to sub-zero in and I want to start differentiating things. Okay, so we've got e to the power of sine x. So f of 0 would be e to the power of sine of 0. Sine of 0 is 0. E to the power of 0 is 1. Make sure you show this because obviously the answer is provided. We need to justify where this is coming from. Okay. Now let's differentiate. So when we go to differentiate this, we're basically using the chain rule. Like we've got a function inside another function. And if you can remember your shortcut for exponentials, you look at your power. If you differentiate the power, you get cos x. So you'll multiply by the derivative of the power. Essentially the rule I'm using there was if you've got e to any function of x, the derivative is just f dash e to the power f of x. You can obviously use the chain rule. You can do a substitution, but if you want to try and do these quite quickly, because we're going to be doing a fair amount of differentiation, like you could say y equals e to the u, and u equals sine x, and dy by du is e to the u, du by dx is cos x. And remember, that's how the chain rule works. If you want to figure out dy by dx, if you've got dy by du and du by dx, you can just multiply them together. But, you know, let's just remember the shortcuts, because we'll be doing enough of them. So there's our first derivative. Okay, now we need to figure out what the first derivative evaluates at 0 is. So if you sub 0 into cos, you get 1. Sub 0 into sine, you get 0. E to the power 0 is 1. 1 times 1 is 1. Again, this is a show question. Like we're aiming to end up with this answer. So show that like you've differentiated clearly show that you've sub 0 in. Okay. We need to get up to the x squared coefficient. So we're gonna have to differentiate again. Now, be careful here because look at what we're differentiating. We've got cos x e to the sine x. We're clearly going to have to use the product rule for this. Okay, product rule is u times by dv plus v times by du. Another way of thinking about it when you've got two functions, differentiate one, leave one alone, then differentiate the other one, leave that one alone. So we've got u, which is cos x, times by the derivative of this, which is cos x, e to the sine x, plus, okay, so we left that one alone, we differentiated that one. Now let's differentiate this one, so it'd be minus sine x, e to the power of sine x. Can we tidy this up at all? So we've got a common factor of e to the sine x, so that would be cos squared minus sine x, e to the power of sine x. And we need to just substitute 0 in, because we need to get our series expansion. So f double dash of 0, cos of 0 is 1, so cos squared is 1 squared minus sine of 0, which is 0, e to the power 0, which is 1, so we've got 1 squared minus nothing, times by 1, we've got 1. So now that we've evaluated our function and our derivatives at 0, remember we're using this formula for the series expansion. So we can say that therefore e to the sine x would be equal to f of 0, which is 1, plus f dash of 0, which is 1, plus the second derivative evaluated at 0, which is 1, divided by 2 factorial x squared, which is 1 plus x, plus a half. x squared. It also wants us to show that the x cubed coefficient is 0, which is particularly mean because now we're going to have to get the third derivative if we want to get the x cubed coefficient. Okay, so let me clear a bit of space and we'll think about how to get our third derivative. Okay, so we know our second derivative is this, and we're going to have to do the product rule. Okay, it's getting to that level of complexity where I might not do this in my head, I might sort of do a bit of working out, so I'll say u equals cos squared minus sin, and v equals e to the sin x. So dv by dx would be cos x e to the sin x. When we differentiate this one, du by dx, again we're doing the chain rule. There's a function inside a function, so you can do a chain rule question, but try and remember the shortcuts. Okay, so for a bracket to a power, times by the power, differentiate what's inside, which would be minus sin x, and then take one off the power. Okay, so times by the power, times by the derivative, take one off the power, minus sin x would become minus cos x when we differentiate. Okay, let me just maybe tidy this up a little bit. We'll take it back to a cos x off. That would be minus 2 sin x minus 1. Could have taken the minus out as well, couldn't I? Anyway, third derivative. So u times by dv and v times by du. So we're going to get cos squared minus sin times by cos e to the sin x plus v times by du, which is cos x minus 2 sin x minus 1 e to the sin x. Okay, so we need to show that the x cubed coefficient is 0, so we're going to show that this is equal to 0. Let's see. So when we sub 0 in, you've got to justify a little bit of working out here. You can't just write equal to 0, okay? So cos is 1, so that would be 1 squared minus sine of 0 is 0. Cos of 0 is 1. E to the 0 is also 1. And then plus cos of 0, which is 1. Minus 2 times 0, so that would be 0 minus 1. And then e to the 0. So what have we got? 1 times 1 times 1. We've got 1, 1, minus 1, 1, 1 minus 1 equals 0. So you could say therefore, as the third derivative is equal to 0, our x cubed coefficient must equal 0. All we've got to do now, we've done the hard work, okay? Last part of the question, we want to evaluate this limit. And think about how this question's set up. Like, this is not like a brand new question. It's not like, oh, by the way, do all this stuff and then, oh, there's a random limit at the end. Like, the terms that we're being asked about here, we have already done quite a lot of work with. Like, we know what the expansion for e to the sin x is. We know what the expansion for ln of 1 minus x is. So let's sub in each of these series expansions and then see what happens. So we've got the limit as x tends to 0 of e to the power of sin x, which is 1, plus x plus a half, x squared minus 1, plus ln of 1 minus x, which is minus x, minus a half, x squared minus a third x cubed minus a quarter x to the 4. And then this is all being divided by x squared sine x. And don't leave it as x squared sine x, because if you leave it as x squared sine x, you won't be able to cancel anything down. Like, don't forget we also know a series expansion for sine x, but that's one of our shortcuts that we get in our formula booklet. So we could say sine x was x minus x cubed over 3 factorial, which you could write as 6 plus x to the 5 over 5 factorial, which would be 120. Okay, so it looks like a bit of a mess. Let's tidy this up and see what we've got left. Limit as x tends to 0. So we've got 1 minus 1, we've got x minus x, we've got a half x squared minus a half x squared, so actually we're left with minus a third x cubed minus a quarter x to the 4. And that's all divided by x cubed minus a sixth x to the 5 plus 1 over 120 x to the 7. And now that we've got to this point, because we're trying to evaluate the limit as x tends to 0, before you can evaluate the limit, so once you've got it in this form with the series expansion, you're just going to cancel down whatever powers of x that you can cancel. And if you notice here, because a lot of stuff cancelled out, you can divide everything by x cubed, like you can cancel throughout by x cubed. So we'll say that would be the limit as x tends to 0 of minus a third minus a quarter x 1 minus 1/6 x squared plus 1 over 120 x to the 4. And all of these terms that we forgot, like the x to the 5s and so on, that we didn't write down, like it doesn't matter that they're not there, like just the same as on the denominator, because remember what we're trying to do is we're trying to evaluate the limit as x tends to 0. And all of the rest of the polynomial, which still has x terms left in, they would all tend to 0, and we're going to be left with the constants as x tends to 0. And the answer would just be minus 1/3. Okay, so I suppose if I had to give myself enough space, we could set this limit out of the original question, say therefore the limit for this as x tends to 0 would be equal to minus 1/3. One sort of thing that I didn't mention while we were doing it, because I didn't want to like overcomplicate it, there is a significance to what you've done here. You know, when you say in fact that the x cubed coefficient is 0, it's quite important, because like if you look here, we worked out e to the power of sine x, the expansion for e to the power of sine x. So these terms here were the e to the power of sine x, and that significantly has 0 x cubes. Because if you think about it, if that x cubed coefficient wasn't 0, like if this series expansion for e to the sine x would have had some x cubes in it, that would have had an impact on our final answer, because all that other stuff cancelled and you had minus a third x cubed. So if that would have had a coefficient as well, the final limit would have been a combination of those two things, because that's essentially, this is where our limit comes from. Everything else cancels out, doesn't it? Okay, so just bear that in mind. There was actually a reason for them making us do that pretty horrific derivative. Okay. Lot going on this, but it's a sort of a standard technique. You know, get good at differentiating things so that you can do your series expansion, and then once you've got your series expansions, just sub them in. Key step on this is to show that you've cancelled all the x terms down. So write all your series expansions in, cancel all the x's that you can, and then don't forget to write equals to at the end. Don't say it tends towards, like make sure you write equals. Alright, thanks guys.